What is a porphyry magmatic system? A porphyry magmatic system is a large-scale geological system that forms around intrusive igneous bodies, usually associated with calc-alkaline magmas generated in convergent tectonic settings such as subduction zones. These systems are best known for producing porphyry type ore deposits, which are among the world's most important sources of copper, molybdenum, gold, and other metals. At the core of a porphyry magmatic system lies a magma chamber emplaced in the upper crust. As the magma evolves, it differentiates into two key components, a crystalline-rich magma and a volatile-rich fluid phase. The crystallizing magma often produces porphyritic intrusions, which are characterized by large crystals, phenocrysts, set in a finer-grained matrix. These porphyritic intrusions not only provide the name for the system but also play a crucial role in ore formation, as they act as both the heat engine and the source of mineralizing fluids. A defining feature of porphyry magmatic systems is the exsolution of hydrothermal fluids from the cooling magma. As pressure decreases during magma ascent, volatile components such as water, carbon dioxide, chlorine, and sulfur separate from the silicate melt. These fluids become enriched in metals and migrate into the surrounding host rocks, where they precipitate ore minerals in a network of stockwork veins, veinlets, and disseminations. The interaction of these hot fluids with the surrounding rocks also produces characteristic hydrothermal alteration zones, potassic, phyllic, argillic, and propylitic, which geologists use as exploration guides. In addition to ore formation, porphyry magmatic systems are dynamic and long-lived. They may undergo multiple intrusive and hydrothermal events over hundreds of thousands to millions of years. The upper parts of the system can also be linked to epithermal deposits, while deeper parts may connect with skarn or carbonate replacement deposits, showing that porphyry systems often act as the central hubs of larger mineralizing provinces. Because of their scale, abundance, and economic importance, porphyry magmatic systems are studied not only for resource exploration but also for understanding fundamental processes of magma evolution, fluid exsolution, and crustal differentiation. They are critical in shaping both the geological and economic landscapes of many regions around the world. How is a porphyry magmatic system formed? The formation of a porphyry magmatic system is a complex, multi-stage geological process that takes place primarily in convergent tectonic settings, such as where an oceanic plate subducts beneath a continental plate. These tectonic environments provide the necessary heat, pressure, and geochemical conditions to generate large volumes of metal-rich magma and the hydrothermal fluids that eventually create ore deposits. The process unfolds through several interconnected stages. 1. Subduction and magma generation. The foundation of a porphyry magmatic system begins with subduction. As an oceanic plate sinks into the mantle, it carries with it sediments, seawater, and altered oceanic crust. These materials release fluids into the overlying mantle wedge, lowering its melting temperature and generating calc-alkaline magmas. These magmas, enriched in water and volatile elements, rise buoyantly toward the crust. 2. Magma storage and differentiation. As the magma ascends, it stalls in the mid to upper crust and begins to accumulate in magma chambers. Here, repeated injections of fresh magma create large, long-lived reservoirs. Within these chambers, crystallization and differentiation occur. Early formed crystals separate from the melt, causing the remaining liquid to become progressively enriched in volatiles, silica, and metals such as copper, molybdenum, and gold. Over time, this evolving magma body becomes the engine of the porphyry system. 3. Exsolution of volatile-rich fluids. One of the most critical steps in porphyry system development is the exsolution of fluids. As crystallization progresses and pressure decreases, water and other volatiles, CO2, S, Cl, F, become oversaturated in the magma. This leads to phase separation. A magmatic-hydrothermal fluid rich in metals is released. These fluids are less dense than the surrounding melt and migrate upward, creating fracture networks that allow for further fluid movement. 4. Porphyritic intrusions and fracturing. The ascent of small, porphyritic intrusions, dikes and stocks, provides both pathways and pressure release zones for the escaping fluids. These intrusions are characterized by large phenocrysts in a fine-grained matrix, giving rise to the term porphyry. The emplacement of these intrusions generates fractures and breccias in the surrounding rocks, greatly increasing permeability and providing space for hydrothermal fluids to circulate. 5. Hydrothermal alteration and/or formation. The exsolved fluids are hot, acidic, and metal-rich. As they ascend and interact with cooler host rocks, they cause intense hydrothermal alteration. This alteration occurs in distinct concentric zones. Potassic alteration near the core, K-feldspar plus biotite, associated with copper-gold mineralization. Phyllic alteration, quartz plus cerussite plus pyrite. Argillic alteration, clays, kaolinite, montmorillonite. Propylitic alteration, chlorite, epidote, carbonate, on the outermost fringes. Or minerals such as chalcopyrite, bornite, molybdenite, and gold precipitate in stockwork veinlets, breccias, and disseminated halos, forming large, low, to medium-grade but highly economic deposits. 6. Link to epithermal and other deposits. The upper parts of porphyry systems can give rise to epithermal gold and silver deposits, while deeper parts may be connected to skarns or carbonate replacement deposits. This vertical and lateral zonation reflects the evolving chemistry and temperature of fluids as they rise and mix with meteoric waters. 7. Longevity and cyclic nature. Porphyry magmatic systems are not instantaneous, they develop over long timescales, often hundreds of thousands to millions of years. Multiple pulses of magma injection, intrusion, fluid release, and fracturing can occur, producing overlapping alteration zones and/or forming episodes. This cyclicity is why porphyry deposits are so large and continuous, often containing billions of tons of mineralized rock. Summary. In essence, a porphyry magmatic system is formed through the interaction of subduction-related magmatism, magma differentiation, volatile exsolution, and hydrothermal fluid circulation. The result is a vast mineralizing system that not only provides critical global resources of copper, molybdenum, and gold but also offers key insights into crustal processes, magma evolution, and the role of fluids in Earth's geology. What are the characteristics of a porphyry magmatic system? A porphyry magmatic system is a distinctive geological system with a set of recognizable characteristics that make it unique, both as a geological phenomenon and as the world's most important source of copper, molybdenum, and gold. These systems are not simply ore deposits, they represent large, long-lived magmatic hydrothermal complexes that influence a wide portion of the Earth's crust. Below are the main characteristics, explained in detail. 1. Large-scale and long-lived systems. Porphyry magmatic systems are regional in scale, often extending several kilometers in diameter and several kilometers deep. They are not short-lived events but persist over hundreds of thousands to millions of years. Multiple pulses of magma intrusion, fracturing, and hydrothermal activity can occur, resulting in overlapping alteration and mineralization episodes. This longevity explains why porphyry systems produce such massive ore deposits. 2. Porphyritic intrusions as the magmatic core. At the heart of these systems are porphyritic intrusions, igneous bodies containing large crystals, phenocrysts, set in a fine-grained groundmass. These intrusions form from water-rich, calc-alkaline magmas that ascend from mid- to upper crustal magma chambers. They serve as both the heat source and the fluid source, releasing volatile-rich fluids during crystallization. The geometry of these intrusions, stocks, dikes, breccia pipes, controls the distribution of hydrothermal fluids and ultimately the pattern of mineralization. 3. Exsolution of metal-bearing fluids. One of the defining features of porphyry magmatic systems is the release of large volumes of hydrothermal fluids from the crystallizing magma. These fluids are enriched in water, sulfur, chlorine, and metals such as copper, molybdenum, and gold. Their migration into fractures, faults, and permeable zones is critical for ore formation. Because of this, porphyry systems are described as magmatic hydrothermal systems, where both igneous and hydrothermal processes are intertwined. 4. Extensive hydrothermal alteration. Porphyry systems are surrounded by broad zones of hydrothermal alteration, typically forming concentric or overlapping shells around the intrusion. These alteration zones are key exploration indicators. Potassic alteration, K-feldspar, biotite, magnetite, located near the core and associated with copper-gold mineralization. Phyllic alteration, quartz, cerussite, pyrite, often forming a halo around the potassic core. Argillic alteration, clay minerals, kaolinite, smectite, common in shallower parts. Propylitic alteration, chlorite, epidote, carbonate, extending to the outermost zones. These zonations reflect the cooling and chemical evolution of hydrothermal fluids as they disperse outward from the intrusion. 5. Or mineralization style. Porphyry magmatic systems typically host ore minerals in stockwork veinlets, disseminations, and breccia fillings rather than in massive, concentrated bodies. The main ore minerals include chalcopyrite and bornite, copper. Molybdenite, molybdenum. Native gold and electrum, gold. Pyrite, as a common gangue and exploration guide. Although individual grades may be low, often less than 1% Cu, the enormous volume of mineralized rock makes these deposits highly economic. 6. Zonation of metals. Metals within porphyry systems often display vertical and lateral geochemical zonation. Copper and gold tend to concentrate near the central potassic zone, molybdenum often occurs at deeper levels, and lead-zinc-silver may appear in more peripheral or shallower settings, sometimes linked to overlying epithermal systems. This metal zoning provides valuable clues for exploration and understanding ore-forming processes. 7. Structural control and fracturing. The architecture of porphyry magmatic systems is strongly influenced by fractures, faults, and breccias. The emplacement of porphyritic intrusions generates pressure, causing rocks to fracture. These fractures act as fluid pathways, allowing hydrothermal solutions to permeate large volumes of rock. As a result, ore distribution often mimics stockwork vein networks and breccia zones, with mineralization intensity depending on fracture density. 8. Relationship with other deposit types. Porphyry systems rarely exist in isolation. They often serve as the central hubs of larger mineralizing provinces. For example, epithermal deposits can form above porphyry systems at shallower crustal levels. Skarns and carbonate replacement deposits may develop along the margins where fluids react with carbonate host rocks. This vertical and lateral connection between deposit types shows the integrated nature of magmatic hydrothermal systems. 9. Geodynamic setting. Most porphyry magmatic systems form in subduction-related arcs, such as the Andes, the Philippines, or the American Cordillera. However, they can also occur in collisional and post-subduction settings. Their presence is closely linked to plate tectonics and the long-term cycling of volatiles and metals from the mantle into the crust. 10. Economic importance. From a practical standpoint, porphyry systems are the world's largest sources of copper and molybdenum, as well as significant producers of gold, silver, and rhenium. Their size, relatively predictable alteration patterns, and broad metal zoning make them the backbone of global metal supply. In summary, the characteristics of a porphyry magmatic system include large size, porphyritic intrusions, volatile-rich fluid exsolution, concentric alteration zones, stockwork style or mineralization, structural control by fractures, and geochemical metal zonation, all hosted within a tectonic setting driven by subduction-related magmatism. These features make porphyry systems not only geologically fascinating but also economically indispensable.